Okay, so today I'll be giving you the big picture of inductance. I'll be answering all of these questions working around clockwise, giving you a sample problem, walking through it with you, and then giving you a chance to do a practice problem on your own. So be sure to pause your video and try it out. So, what is an inductor? An inductor is a conductor, think of a copper wire, wrapped around another piece of metal, like an iron nail. It's symbolized like this. For each type of inductor, there is an equation that is specific for its magnetic field. For a solenoid, magnetic field is equal to the permeability of free space, which is a constant, multiplied by the number of turns in the coil over its unit length, which we will label as H, multiplied by current. We'll come back to that. So let's finish this, create a circuit, and see what the relationship is between a change in current and the behavior of an inductor. We'll put a battery right here and a variable resistor right here. We know that if we change the resistance, there will be a change in current because V equals IR. Let's say that we increase the resistance. That will decrease the current. We know because of this equation that a change in current will change the magnetic field. That will cause it to decrease. To understand the next part, we need to go to Faraday's law. So a derivation of Faraday's law is that the magnetic flux is equal to the magnetic field multiplied by cross-sectional area times cosine theta. Faraday's law itself states that an EMF is equal to negative n being the number of turns, times d magnetic flux, the rate of magnetic flux, over the rate of change in time. So, looking back here, if we have a decrease in magnetic field, that means that there's going to be a decrease in flux. And if there is a decrease in flux, that means there will be a positive EMF. If there's a positive EMF, that means there's going to be a voltage. A voltage will make the inductor behave like a battery. We'll come back and explain what direction that EMF is traveling. So, what is inductance? I'd like to thank LASSEVIREN1, you can find his channel on YouTube, for providing this amazing example. If we take Newton's second law, force equals mass times acceleration, we'll write that as a change of velocity over time. We can find out what inertia is. Inertia is the resistance to a change in motion and is dependent on the mass. If mass increases, so the mass is large, then there'll be a greater inertia. The inertia will be large. And if the mass is small, the inertia will also be small. The electrical equivalent involves inductance. Our EMF, or our voltage, induced voltage, is equal to negative L, the inductance, times the change in current over change in time. This is like our electrical inertia. If we have a great value of inductance, then it will greatly oppose any change in current. Let's write that down. This is important for your notes. Inductance is the ability to resist a change in current. A large current, or a large inductance, will greatly oppose the change in current. And a small inductance will not as greatly oppose the change in current. Now, how is this helpful to help us know the direction of an EMF? Let's draw an example. This is our inductor. Let's say that current is flowing this way. Well, if current is just flowing, there's no change, and there is zero EMF. But if current were to increase, then the direction of the change in current is that way because it's increasing. To oppose that, it will induce an EMF in this direction. To write that, we'll write it like this. Remember that the big line tells you which direction it goes out, so the current will go this way. This is only brief. It's only during the period of change in the current. If we have another example, the current is flowing this way, but it decreases, that means that the change in current is in this direction. And to oppose that change in current, the EMF will be in this direction. This will help us out in solving practice problems. How do we derive inductance? This helps us understand the behavior of inductance and what causes it to be greater or lesser. EMF is equal to N, rate of change in magnetic flux, over change in time. This is Faraday's law. If we go back here and take our magnetic flux and substitute it in here, then we have negative N is equal to our rate of change in BA over time. We also have an equation for magnetic field, which can be substituted in. That is equal to negative N, and then we'll have our rate of change in, for a solenoid, permeability of free space, N over H, times current, multiplied by our cross-sectional area over time. Now this is getting kind of dense, so let's simplify it by taking out all of our constants. We have our EMF equal to negative N mu naught N over H times our cross-sectional area. And all that's left is our rate of change in current over time. Well, this is very similar to our equation for inductance. That means that all of this right here is equal to L. How does that affect the behavior of inductance? Well, N is the number of turns in the solenoid. So if there are a greater number of turns, then we have a greater electrical resistance to change in current, or a greater inductance. If there is a lesser cross-sectional area, for example, in our solenoid, that means that the inductance is less and it will not as greatly oppose the change in current. Let's look at the units. EMF is equal to negative L, change in current over time. Well, if we divide by the change in current over time, we can get the units of inductance. So L is EMF over negative di over dt. Well, what are the units? It's voltage over amperes per second. For example, if we have this is called a Henry, volts over amperes per second. If we have a 10 Henry inductor, that means that there are 10 volts that pass for every ampere per second. If we were to have half as many amperes per second, so we would have 10 volts over amperes per second, and we only had 0.5 amperes per second, that would mean that we would have an induced voltage of only 5 volts. Okay, let's move on to a practice example. We'll draw our circuit. We'll draw in a strong resistor, our battery, a resistor right here, and our inductor. We'll call that 5 henries. When we close this portion of the circuit, we'll call that 1, and this portion we'll call 2. So for any of these practice problems, the first thing you'll do is you'll draw a graph of current versus time. So the second we close this circuit right here, the current created from the battery will start to increase before leveling out. Well, let's look at what's going on. The voltage across this resistor at time equals 0 is going to be 0 because V equals IR. And at time 0, there's no current. So the voltage across it is equal to 0. The voltage across the inductor is not equal to 0 because our induced voltage is equal to negative L times di over dt. di over dt is the rate of change in current, which is a slope, and there's a great slope right here. That means that all this voltage right here is accounted right here. Now, what's the direction of the induced current? The induced voltage. The induced voltage will be in this direction. Now, why? Because there's an increase in current in this direction, and it opposes the increase in current, so it will be in that direction. Okay, now we can find what the current is across this at time equals infinity, after it has leveled out. The current can be found using V is equal to IR. V is equal to IR, and so we can say the current is equal to V over R, which is 10 over the resistance right here, 2. So the current flowing through, once it's stabilized, is 5 amps. Now, this is part 1. Moving on to part 2. On part 2, when we close this part, there is a net decrease in current because it's no longer connected to the battery. We get a graph that looks like this. So at time right here, t is equal to 0, let's find what the voltage is across this resistor. V is equal to IR. We have a high current right here. It's the same as what we solved in part 1, 5 amps. So the voltage is equal to 5 times 100, because we have a 100 ohm resistor, and that is equal to 500 volts. The voltage across the inductor is also 500 volts. Okay. Now, what is useful about this is that we can find two things. One, we created a much larger voltage across this resistor right here. We started with a battery of only 10 volts, and now we have a very large voltage. In application, this is very useful, for example, in cars, because cars, you need a large voltage, and that can create a spark to start the engine of the car. We can also use this information to figure out what the rate of change in current is. That can be solved by using EMF is equal to negative L, change in current, over change in time. We know what L is, and we know what the EMF is. It's 500 volts. So all we do is take 500, divide by negative 5, and that gives us negative 100. So that's the rate of change in current, amperes per second. Sorry that was a little crowded, but I have another example for you that you can work on. Go ahead and pause your video and answer these questions. Okay, this is organized the same way as the previous practice problem that I did with you. And if we go ahead and solve, here are the answers to that second practice problem. There you have it. That's inductance. I hope this was helpful to understand that inductance is the ability to oppose a change in current, that changing the cross-sectional area or the number of coils will affect the inductance, and how you can solve a practice problem by looking at graphs of current versus time. So go forth, prosper, and be successful.